we will now prove the relational laterality law. Most frequently, the relational laterality law is used with this kind of type signature of a function. And then the law has the form for any two values of this type, such that they are in the relation lifted to P, the function T of P and the function T of Q is in the relation lifted to Q. So this is the form of the law that is most often used in practice, but this is not convenient to prove in this form. And I will show why. Instead, it is more convenient to consider an expression of some type f of a. And it's the same to say that this expression T of A satisfies the relation T of A, T of B is in the relation R lifted to F. And this is equivalent to this, because if F equals P to Q, then this is going to be the pair function mapper to lift, and that's exactly the same condition as this. However, if you try proving this law, you will have to look at the code of the function t, or the expression t. So the expression t will have to be fully parametric. It has to be implemented by some fully parametric code. And this code will have parts that are not necessarily of the same form. And that is the difficulty that we're going to overcome right now. So consider, for example, the function of this type for all A, from A to pair of AA. The code for this function, let's write this in Scala. So from X to pair of XX. Now, suppose we want to prove that this function satisfies the appropriate law. So we will have to look at the code expression here. And this code expression is a function. So we'll have to look at the function body, and we will have to use an inductive assumption that if the function body satisfies the relational laterality law, then we will prove that also this function satisfies that law. This is how we will have to prove by induction. And in order to prove that this sub-expression satisfies the law, we will have to assume that the two parts satisfy the law, and then we will show that if the two parts satisfy the law, then the tuple also satisfies the law. So this is how the proof will have to go, because that's a proof by induction on the structure of the expression that we are considering. However, if you look at this expression alone, right, this expression does not have a type of a function. And also, this expression has a variable x that is not defined inside that expression. So it's a kind of an externally defined variable, which in the programming language theory is called free variable. It's a free variable. Now, this terminology, free variable, is not particularly illuminating. It's not clear what is the free of, is it free of something, or can it be freely used or something like that? It's not clear. So this is not a very well chosen terminology in my way, but this is always the case in science. The terminology is chosen in some arbitrary way. It's not usually not helpful. So let's just keep in mind that free variable means a variable in an expression that is defined outside that expression. It should be defined outside that expression and not inside it. So in this whole function, the variable x is defined inside it. It's a function of the argument x, so x is defined inside it. But if you look at this sub-expression, then x is not defined inside that sub-expression. So for this sub-expression, x is a free variable, or variable defined externally. Now, for variables defined externally, you need to have a special provision because they will have some type, and this type could depend also on the type A, on the type parameter A. And so, just like in this situation, x is of type A. So it is not just some fixed value, it's actually a value of type A. So if you are talking about expression T of A and expression T of B, then this x inside that expression will be a different x. It will have a different type. In this one, it will have type B. It will be a different value. So you have to explicitly talk about that. So what are the free variables? What are they equal to? What type they are? And in what relation are those types? And the result is that we are going to formulate the relational with a free variable, with, let's call it z. So then we will write the expression like this. So T of A of z, so that z is used inside T. So this entire expression has type Q of A, but z is a variable of type P of A, where P of A is a different type constructor. And the z is used in some way to build up the expression T of A. Just like this here, the variable x has type A, and it's used to build the tuple xx. So we will then formulate the law like this. It's if you have any fully parametric expression of this kind, and for any relation R between A and B, and for any two values, Z1 and Z2, of types P of A and P of B, if these two values are in the lifted relation to P, then the T is in the lifted relation to Q. So this is just the same as the function mapper, the pair function mapper, because this is a function of Z. So this is the law of T, where we consider T as a function of Z. So if T were actually a function of Z, which it is not, it is an expression that uses Z, right? And there's a slight difference. If you have a function of Z, which looks like Z goes into, say, Z, Z, Z. That's a function of Z. Or you have just the expression Z, 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 which is the body of that function, but it's not itself a function, right? So we do not want to restrict ourselves to always talk about functions, but so we have to consider expressions that are not functions like this. But in some sense, they're equivalent to this function being applied to a value Z, right? So, and the law for this function is the pair mapper law. And so when we apply to Z, then we are in the right-hand side of this law, so to speak. So we're here. So that's why the relational law can be reformulated like this. And that's equivalent if you think that T is a function equivalent to this expression. But we are going to always write like this, T of Z. So this applies to expressions containing one free variable. If you have more free variables, you can put them into a big tuple, and you will then get the same results, just a different type of variable. So now, what is going to be the proof? We are going to say that we're going by induction on the structure of the code of this expression. At top level, this expression must be built up of one of the 9 code constructions. And each construction will have to decompose this code somehow into one or more sub-expressions. And for each of these sub-expressions, which will have the same shape, will be again some code that uses some free variable or the same free variable or more free variables. And the inductive assumption is that the relational neutrality law, or the parametricity theorem, so this theorem says that it satisfies the law. So the theorem holds for all the sub-expressions and also for the free variable z. So the free variable z will be always assumed to be some values z1, z2 in a relation. We can then choose these two variables for each inductive case and formulate more quickly. But basically, we will always have some variables z1, z2 that are in the relation. And for these variables arbitrarily chosen, we'll have to prove that the entire code expression is in the relation lifted to Q, as long as each sub-expression satisfies the same law for its respective type. So let's go through the proof. So the first case is a constant type. So when it's a constant value of some fixed type, then the lifting to that is an identity relation. And z is irrelevant because it's a constant function, does not depend on z. And so it's just an identity relation. And that's obviously c, and c is in the identity relation. It's the same value. As t of b and t of a are going to be the same, going to be just a constant. And so then this holds. The second case is when we use the arguments. Now this case did not actually use the argument. It was a constant value, and this uses the argument. So that argument has type P of A, and so T of A also has type. T of Z also has type P of A. So it's P and Q are the same. So remember, we always say that here, T of Z has type Q of A, and Z has type P of A. And so in this case, because T of Z equals Z, P and Q are the same. And so then this condition becomes identical. If Z is in that, then again, Z1, Z2 is in that same relation. So that folds. The third case is when we create a function. So how do you do that? Well, you write an expression, a code, which looks like this, going from some h, a new variable h, to some code, which is the body of this new function, which will be an expression depending on z and h. Now, these are two free variables, right? So now h could be of a different type. S could be also of a different type. And the type Q here is a type of T of Z is H of A to S of A. Where H and S are just arbitrary new different type expressions. Now, what we need to prove is that if Z are in those relations and H1 and H2 is in this relation, then S of Z1, H1, S of Z2, H2 is in that relation. So that's what we need to prove, because that's going to be the pair mapper of this type. And if we prove that, that's the same that T of A Z1, T of B of Z2 are in the relation R map Q of R. So that's the same as this. But this holds because this is just the inductive assumption for S. S is a function of two free variables. And so we consider this as a tuple. And the inductive assumption for this is that it satisfies its relational neutrality law with two free variables, which is a tuple of this kind. So then it's this and this must be in their relations. That's just the same as the inductive assumption that S satisfies its law. So then this holds. The fourth case is when we use the function. So we have already some function g, and we have already some value h. We apply g to h, and that's the code of t. Now g is again possibly depending on the same free variable z. And it has this type where h is arbitrary and h is the type of h. So these are the two sub-expressions now. The inductive assumption is that both of these sub-expressions already satisfy the law. So now we have to see what these inductive assumptions are. So if z is in that relation, then h is in this relation, lifted to h. If h is in this, so the function g of z satisfies the pair mapper. Now this I should say here to be quite pedantic. This is here g of z. This is here g of z. So g of z has this type. And so its relational neutrality law is that if the arguments are in this relation, then the results are in that relation. So if we just put this together, we have what we need. If this is true, then this is true, but then if this is true, then this is true, and that's what we need. Because here's z1, z2, g of z1, h1 is the same as t of c1. So that's, for example, and that's therefore the same as what we need to prove. So going on, the fifth case is to create a tuple. Now, here we have a function, an expression t that is made of two sub-expressions u and v. And then u is of some type u, v of some type v. And what we need to prove is that this is in that relation. Now, the big Q is just a tuple of two of u and v here. So that is the case 5. By definition of lifting, the lifting of 2Q is a pair product of these two. And so if we write out what that means, the two values of t are in this relation when the two u's are in this relation and the two v's are in that relation. But that holds by inductive assumptions. The inductive assumptions are that u and v already satisfy the law. So when z1 and z2 are in that relation, then this holds and this holds. So these are inductive assumptions, and this is directly translated into what we need to prove. In case 6, we use a given tuple. So we have an expression, G, which has a tuple type. And this expression is used by taking the first part of the tuple, let's say. And then let's say we have this type, G, which is a tuple of Q and R is something else. Doesn't matter what, because we're dropping it in this code. So by the inductive assumption, the G satisfies its law, but the lifting to G is this pair product. And if the lifting to G is this pair product, we can translate that by saying that, well, the pair product says that the first pair must be in its relation, the second pair must be in its relation. So it means that the first part of the tuple must be in this relation, and the second parts of the tuple must be in this relation. Well, the second parts of the tuple we don't need, and the first parts are in the relation that we require. And so that proves that this expression satisfies the law. And when it's the second part of the tuple, it's a very similar proof. The next case is when we create a coproduct. Now, let's say we create a left of some here sub-expression, and this sub-expression has some type G of A. And so we assume that our type Q is an either of G of A and H of A. where H is some other type, but we're not going to use since we're creating just a left. So then this sub-expression of type G by assumption satisfies already the law. So the G of Z1, G of Z2 is already in this relation. But then the left and left are in that relation because that's the pair sum. The pair sum is that these two values must be both on the left and those values must be in the relation, or they must be both on the right. They must be. But now we have the left, so that's good enough. Similarly, okay, this is a mistake. This must be right. When it's right, then it's a very similar proof. The next case is to use a coproduct. This is a pattern matching rule where we have three sub-expressions. One is this S of Z, which has type of either G of A and H of A. And then we have pattern matching for left and right cases. The result of pattern matching are some expressions here, which I denoted by U and V, where U of Z is a function from G of A to Q of A, and V of Z is a function from H of A to Q of A. Now we could have also written this proof using free variables of tuple like this. So where we have sub-expressions depending on the tuple. Now this is equivalent. I'm just not going to do that, but this could be equivalent. So the inductive assumptions are that the functions U, S, and V already satisfy the law, which, for example, means that when Z satisfies that law, when there are some values x1 and x2, which are here, then U of Z1, x1, U of Z2, x2 are in the relation lifted to Q. Now, Q is a result type of this entire pattern match. So this is of type Q of A, and this is also of type Q of A. So this is an inductive assumption for U and an inductive assumption for V, the same, will be similar. Now, the inductive assumption for S also needs to be used, and that is that the function S of Z1 and S of Z2, that is in the lifting to S, which is the pair sum of lifting to G and lifting to H, which means that either S of Z1 and S of Z2 are both in the left side or both in the right side. And if they're in the left side, then the values they're wrapping must be in that relation. If they're in the right side, then must be in that relation. So now if you write down what that means, then it means that this is in the relation R map Q, because the preconditions of the inductive assumption here and here are satisfied, because x1 and x2 are in the relation that we need it to be, R map G of R, by inductive assumption for S. In case they're both left, and in case they're both right, then it's the same for the right part. So that shows that if the inductive assumptions for S are correct and the values are both in the left, then the inductive assumption of U gives us what we need for T. And if they're both in the right, then the inductive assumption for V will give us what we need for proving that T satisfies the law. So then this is to prove the case 8. And finally, there is a case 9, which is a recursive call, which can be written like this. So T is defined recursively. So the code for T uses T itself inside its own expression. So there's some function F, which is a sub-expression, which is applied to the same expression T of Z that we're trying to define here. Now, the function F is of type Q of A to Q of A, and the inductive assumption is that the law holds for that function f, and the law holds for the recursive invocation of the function t, of the expression t of z. So that is the standard way that we prove recursive code properties. We assume that all recursive calls already satisfy the law that we're proving. And so then with that assumption, we need to prove that this entire thing satisfies the law. But that is just the use function rule with two sub-expressions that already satisfy the law. So we are ready to prove that this is also satisfying the law. Note here, we do not need termination. We do not talk about whether this recursion terminates, whether there's an infinite loop or not. If there's an infinite loop, then obviously this code is wrong, and we don't need to prove any properties of that code. We're not trying to prove that it's terminating. We're just trying to prove that when it's terminating, it satisfies some property. So in this sense, we're allowed to just assume that all recursive calls already satisfy this property, because eventually this function f will be evaluated without using the value. So eventually the recursion will terminate, and then this call f of t will not actually use the value t. And so in that case, it's just the law for f that we will need, and that's fine. So that's how we argue in recursive cases. So this completes the proof of all 9 cases, which we have for fully parametric code. And this proof says that whenever you have fully parametric code, that will satisfy the relational naturality law.